If you take here a quick look on my sidebar here, I don't know if you can see it, uh, but 6.1 is area, 6.2 is volume, um, by disk method, then volume by shell method, then arc length, and then we're done with 6. So we're only doing 4 sections. And you see there 6, 7, 6, 6, 6, 6, 7, 6, 8 are projects. Alice, what's your major? Okay, cool. So you'll do the physics project. Noah, physics, right? Everyone else here is computer science, so you're doing the probability project. Okay. Basically, the idea is it's an independent study on each section. So read the section, right? Do the example problems, take a look at the project, do the project. Okay. You probably don't need to wait. You probably do it right away. Okay. So feel free to jump on that whenever you want to. It's basically an application in your field using an integral. So for example, the physics problem is a work problem, right? So, or I think it's a spring problem too, right? So there's a certain K value of a spring. Does that sound familiar? Yeah. Right? So you're finding out how much force is needed to do something. In the probability section, you're just calculating probabilities using an integral. Okay, so the computer scientist, it's actually funny, you could be working for anyone. You could be working for a drug company. You could be working for a hospital. You could be, right, working for aerospace. So you really should be able to do any of it. But I think the probability one is kind of interesting anyway. So there's not much to do today because volumes are tough. The volumes are where we're going to run into trouble. But we'll do a couple of problems from 6.1. 6.1 is very easy. So all we're talking about is area between curves. And of course, how we originally started doing area, right? So there's y1. Here's y2. And so we're simply talking about the area between the two curves. It's that simple, right? So we've got the integral from a to b of y1 minus y2 dx. Now, what we need to do is we need to have a picture of what's going on, because we want to make sure if we start drawing rectangles, right? So I'm going to just pick one particular rectangle there. And I have to make sure that every rectangle I draw, right? And you can imagine me drawing an infinite number of rectangles in that region, right? Or maybe just a few to begin with, right? But I'm certainly going to do the limit as that number of rectangles goes to infinity. And then you'll notice that my width of each rectangle is delta x. And the height of the rectangle, of course, is y1 minus y2 in this case, upper minus lower. So I'm really getting the area as an estimate of the sum from n equals 1 to infinity. Those are the rectangles, right? Sorry. Of the areas, which is y1 minus y2 times delta x. Okay, what I want to look at, though, is I have to be able to see that the height of my rectangle is from one function to another function. It cannot be from one function to itself. I have to be able to calculate. So in this particular case, right, I have an upper minus lower. Times a delta x. But I could have right minus left. So for example, in this case, you can see that my rectangle, and no, let me know if you can't see this. If I draw my rectangle here, it's hitting the same function top and bottom. That can't happen. But in this particular case, if I change my rectangle to this direction, notice it's hitting the purple and the black. So this one's okay. So this one's going to be a right minus left. And then times a delta y. Right? Because if you look at this piece right here, right, that's in the y direction. So usually it'll be forced upon you that you have to do the integral with respect to x or the integral with respect to y. What's really going to help is, of course, that you graph it, okay? Some can be done both ways. And of course, both answers should be the same. So let's just start with a nice easy example. Now the problem with these, to me, is the integration is too simple. So I'll change that for you. I'd rather the integration be complicated, the setup to be simple, and the integration to be like chapter 5. In this particular case, they just have it real simple. The whole thing is real simple, but that's fine. Let's do number 5. So it's telling me my bounds in the y direction and the bounds in the x direction. I would say the most difficult part of this is setting up the integral. These integrals are very easy. So what do I have? I have e to the x from minus 1 to 1. And the other function is x squared minus 1. So it's pretty obvious that the area is upper minus lower, right? You agree? So our integral is from minus 1 to 1 of e to the x minus x squared minus 1 dx. kind of offensive. So what do I get? E to the x minus x cubed over 3 plus x, evaluated at 1 and negative 1. Yes, everybody okay with that? Antiderivative of e to the x is e to the x. X squared is x cubed over 3, and 1 is x. Kind of offensive, huh? Yeah, we get the same thing? Nice. E plus 1 over e plus 4/3. Is that right? Minus 1 over e. So about 3.68. And of course you could double check this, right? On Desmos. And I want you doing that. Yeah, int, the integral from -1 to 1 of parenthesis e to the x minus x squared minus 1, right? Dx, 3.68. So when you're doing your quiz or your test, you're going to know if you have the area right? But you want to still do the integral. Get me as close as you can to a pretty exact answer. To get the decimal, then check it by doing the actual integral on the computer. Let's look at one that's right to left, right minus left. You can kind of see them. Like 9 is a good example of right minus left. So you can see that if it's upper minus lower, I'm going to solve it in terms of y. If it's a right minus left, I'm going to solve it in terms of x. Let's do 7. Y equals x squared and y squared equals x. Y equals x squared. Yeah, y equals x squared. Y squared equals x. Sorry. Now, What's crazy is Desmos is our calculators won't be able to graph this, but Desmos can. So lucky us, we're using Desmos. Y equals x squared and y squared equals x. If you see what would happen if I solved for x in both of these, right? If I solve for x in both of these, I would get x equals what? Square root of y. Yes? And x equals y squared. So, but you can kind of see the x squared curve and the square root curve, can't you? Yeah. So, can I do this one upper minus lower? Yes. I could do either, right? So we're going to do it both ways. So I can go red to black, upper minus lower, or black to red, right minus left, okay? Let's do it right minus left first. So this is y equals x squared. This is y squared equals x. So this one's already solved for me for x, right? Because I'm going to do right minus left. The other one I have to solve for x, I get x equals square root of y, right? Yes, you with me? It is plus or minus square root of y, but it's obvious that I want the positive y out of this, right? Up above the x-axis. So my integral from 0 to 1, because that's where they connect, right? What's interesting is I have to do the bounds in y, right? So I'm trying to find so that the heights match up, right, at 0 and 1, yeah? So integral from 0 to 1 of square root of y minus y squared. Again, I'm doing the right curve, that's purple. Solve for x, right? Solve for x, so square root of y. Yes, you with me? And then minus so light purple minus the dark purple, right? So so this is the one solve for x for the right edge. This is the left edge, right? Right minus left. Okay, this is an easy integral. I get 2/3 y to the 3/2 minus y cubed over 3. Evaluated at 1 and 0. When I evaluate it at 0, they go away, so I just get 2/3 minus 1/3, which is 1/3. I mean, look at what happens to this if I do my rectangle the other way, right? If I do my rectangle this way, guess what? My x bounds are still 0 and 1. The dark purple is the upper curve, but I have to solve for y, so I get square root of x. The other one's already solved for y, I get x squared. Look at it. Same exact problem, right? I mean, there's a lot of symmetry there, so that's sometimes the two integrals will be different problems, but still the same area. Cool. Let's do another one. Um, let's do 15. E to the x and y equals x e to the x, and all they give me is x equals 0. I don't know why, but let's find out. Y equals e to the x. Y equals x e to the x. So they want me to go from 0 to where they connect. Yes, you with me? So it looks like 0 to 1, but I'll double check it. So to double check it, I'm putting the two equal to each other, right? Or set them, right? Yeah, so 1, right? Good, go ahead, do this one. Anybody get there? E minus 2? What's that? Brian, yeah? Nice. Ryan, yes? No? What part? So I did tic-tac-toe for this. Group, yes? You able to get? Yes, nice. Noah, close? Yeah, yeah, yeah. So let's just look at a little theory real quick. Okay. If you remember, we were saying that area is approximately equal to the sum of those rectangles, right? What did I do? Upper minus lower. Delta x, right? And so what happens is when I put that limit on it, right? So I got an infinite number of rectangles. This thing turns into the integral of upper minus lower dx, right? So the sum becomes the integral, the delta x becomes the dx. If I just think of this as some new f of x dx, it allows me, right, or g of y dy, it allows me to use parametric equations as well. So for example, y equals sine of theta, x equals cos of theta. Have you seen that before? Yeah? So watch how I plot my parametrics on Desmos. Well, first of all, what I'd like to do is I'll do something like plot parametric equations on Desmos whenever I'm trying to do something, okay? And it usually gets me a quick link to it right away. And you can see there that I am plotting a point, my xy point, and then I'm telling it how far I want my parameter to go. So look at the parameter here, obviously is theta. Right? And so I probably want to go all the way around a circle, right? So anyway, back to Desmos. I'm going to plot a coordinate point of xy, but my x was cos of theta, right? And my y was sine of theta. Yeah, I'm supposed to use t, I think, for time. There we go. And I want to let it go all the way to 2 pi, right? Well, what do you think? What's the area there? Pi r squared, right? Well, let's see what our calculations do for us. If I have x equals cos of theta, what's dx? Negative sign, right? So taking a look at my integral from 0 to 2 pi of f of x dx, that's y dx, right? Y was sine, and d theta was negative sine. That's a 2 pi of sine squared theta d theta. What's our? You remember this? You remember this one? It's in our Shams, right? Right on that power trig powers section, chapter 22. Oh no, chapter 22 is by parts. Chapter 23 is trig, the very first one. Yeah, it's on page 86. Yeah, yes. So I get the opposite of half of x minus 1/4 sine 2x. And I'm going to evaluate at 2 pi and 0, right? Because like everything's 0. Why am I getting minus half a pi though? I'm screwing something up. Say again?
I'm seeing that sine squared x equals 1/2 1 minus cosine 2x.
Yeah, that's still in the integral, right? And then after you take the integral, you get 1/2 x.
Okay.
I'm screwing something up. I should get pi r squared, right? So that's a radius of 1. I should just get pi. I got opposite of pi over 2. I don't know what I'm doing wrong. It's okay. Let me try another one. Yeah, let's do 37. The area bounded by parametrics t squared and t cubed minus 3t. So my curves are t squared and t cubed minus 3t. I can kind of cheat it a little bit here, right? Obviously from 0 to 1 doesn't get me a complete enclosed area. So I'm going to cheat. I'm going to see what happens if I go to 10. And what if I start at minus 10? Ah, there's the idea. So I see my loop, right? But I went too far, yes? I kind of think I need square root of 3. Probably because I've done the problem before, but let's see what happens if I go square root of 3. There it is, to square root of 3. Oh, there's my enclosed area. I want that area. Now, how do I do this? Is I simply know I have an x and a y, right? So I have x equals t squared, y equals t cubed minus 3t, right? So you can see where this loop hits. X and y are the same. Do you agree with that? By looking at the graph, I can see where I'm hitting at 3. X and y are both 3 there. You agree with that? Right? But remember, I have to find out where t is starting and where t is ending. So first of all, I know that I got a 3 equal t squared. And from there, it's obvious t equals plus or minus rad 3. So that's where I'm getting it from. It's that simple. I can certainly set these equal to each other, right? So that one turned out to be quite simple. But if I set them equal to each other, I can factor out a t. And you already see I have a t is 0. Can I do anything else with it? No. So, but it does tell me another place where x and y are equal at 0, 0. Kind of boring. The trick is knowing that I'm doing the integral in terms of x, that I need the x values, right? And what is my y value? It's t cubed minus 3t, right? And what's my dx value? 2t dt. Make sure you agree with me there. So That's a 2t dt, right? I had a dx there, right? But x is t squared, so dx is 2t dt. So what do I get? 2t to the fourth minus 6t squared. Yeah, you're doing this with me? It's just going to be 2 times that. Because at the square root of 3, it's just going to change all my signs back. Something is happening that's weird. I don't know what the heck is happening. Why am I getting a negative? I'm going to have to look at these problems and maybe save face next class. You should get the, oh, it's the bottom half of the loop. That's why. So I don't want to do this double thing I did because it's giving me the bottom half of the loop. It's giving me negatives. Sorry. Yeah, it becomes positive there. Sorry. That one becomes positive, that one becomes negative. It's two, yeah, it's not wrong. But why am I getting a negative area? All right, I'll figure it out. I will figure it out. Let's see what happens when I do the integral. The integral of negative square root, oops, what did I have for my function? T cubed minus 3t, is that right? T cubed minus 3t times 2t dt, right? Oh, damn it. I know it. I know it now. I didn't change. I don't know what I'm doing wrong. I'll figure it out. I'll fix it tomorrow. I'm sorry about that. Okay, let's look ahead to volumes. So what we're going to be doing tomorrow's the tough class. We're going to be doing a disk method and a shell method. So just to look ahead. So what we're going to be doing is taking some piece. In fact, let's take this piece. And we're going to rotate it around an axis. So for the disk method, we will rotate on an axis that's perpendicular to our rectangle. We want to find that original rectangle, making sure that we're doing upper minus lower, or right minus left. And we're going to rotate around the axis, right? So this is going to be a solid piece, right? Maybe looking like the left edge of a football or whatever, right? And so after I rotate it, right, I've got that solid piece. If it were hollow, it would look like a cereal bowl, right? But it's solid. So I'm taking that area and I'm rotating it around an axis. The disk method rotates perpendicular. The rectangle will be perpendicular. And the shell method has to be parallel. So the rectangle is perpendicular to axis of revolution in the disk method. And we're going to be parallel in the shell method. The disk method is going to turn out to look like a bunch of stacked coins. If you can kind of think of it as afterward, you'll see I have a bunch of stacked coins that are creating, right, my volume. And my shell method, I'm going to have a bunch of stacked circumferences. So when this particular rectangle gets rotated around, I'm going to have an empty, kind of a tuna fish can. So when I do that, when I take that rectangle and rotate it around, I'm getting a circumference. And I'm going to get a bunch of, like the Russian dolls. You see the Russian dolls, you take the one, oh, there's another smaller one inside. So there's going to be a bunch of stacked circumferences here, right? Exactly. Nested cylinders like the Russian dolls, basically. And so you're gonna see a nice little geometry connection there between the two. But the key is to remember shells are parallels. That's the one you have to remember, right? So going back to our first problem today, if I can't draw the rectangle a certain way, I have to go the other way, right? So so looking at the shell method, first of all. Sorry, looking at the disk method. We're going to get our volume from that coin, right? We're going to get a volume from that coin. So think about it. This is the height of the rectangle is the radius of my coin, right? So the volume I'm going to get from the disk method is going to come from pi r squared. And so pretty simple in this case, right? So pi r squared. In the shell method, so this is disk. In the shell method, we're getting our volume by 2 pi r h. So where's the 2 pi r part? So 2 pi r is circumference, right? Okay. So 2 pi r is giving me this measurement around here, right? H is telling me how high that particular piece of the disk is. So there's, right? And then dx is telling me how wide those rectangles are. So nice to look at the two. If you think of a coin, right? That's a circle. So the area of the circle is pi r squared. So this method is that way, and the volume we're using that outside strip of the can. So that I need the circumference and how wide that particular strip is. This is probably the most confusing part of this whole piece that we're going to be doing tomorrow. But you'll see we can really draw nice pictures here to help us understand what the hell is going on. And when we start doing it with functions, we're also going to look at GeoGebra. Let's do that real quick. Let's see if I do disk method. You can really see here the coins stacked on top of each other, right? So each coin has a front area, right, of pi r squared. and then the thickness of each coin is my delta x, or my dx. Let's do square root of x. Right, so that upper curve is square root of x, right? And I'm filling it in. You can rotate. Right, really nice visual, right? It should be, it's a solid. Once I start with a particular area and I move that area around, right, it's going to fill in the inside as well. So the whole idea is that if I cut a cross section of this, right, so I cut a cross section of this, it's clearly a coin, right? And the radius is the height of the function, and the width of each rectangle is my delta x. So pi r squared dx. I think that's a really, really easy one. So the question is going to look like this. Find the volume of y equals square root of x from 0 to 1 rotated about the x-axis. So we certainly want to find the picture, right? So there's y equals square root of x. We want to draw that rectangle, right? And remember, we're rotating around the x-axis. We've got to be perpendicular. A rectangle's got to be perpendicular. So I'd like to try and think about what that whole thing looks like once it's rotated, and what the cross section looks like. It's always going to look like a coin or a washer, okay? And we'll deal with the washer next time. But obviously I get a volume out of this, right? Forgive my 3D ability, but by delta x. So I got my area, pi r squared, right? And then my delta x makes it a volume. So what do I get here? I get pi, I get the integral of x dx. Oh, that's nice. That's x squared over 2, right? So I get pi over 2. Units cubed, right? Who cares about the units? We know it's a volume, right? Now, if we do this one with the shell, With the shell, it's a little bit more difficult, and I'm just jumping ahead a little bit because I didn't want to do too much more today. But if I look at the same one with the shell, I have to be parallel to the axis of revolution. So my rectangle is going to be here. So I have 2 pi times the integral of 0 to 1 I need that rectangle, right? I need that circumference of the rectangle. So how am I going to calculate that piece? It's right minus left. So 1 minus square root of x times, sorry. This is what x equals y squared, right? Yeah. So 1 minus y squared times the height of the rectangle, that's just a y, dy. Okay, so look at that formula, 2 pi rh dy. The radius is how far away that piece of the outside tin can is, right? So that's my arrow, distance from the axis of revolution to the rectangle. And that's obviously starting on the ground, going to some height, so that's a y. And then that piece of that rectangle is still got to be measured, that area, right? So that's right minus left, 1 minus y squared. So what do we get here? Right? Agreed? Y minus y cubed. So I get 2 pi times y squared over 2 minus y to the 4th over 4. You agree with that? When I plug in 0, everything goes away. When I plug in 1, I get 1/2 minus 1/4. So that's 2/4 minus 1/4. That's 2 pi over 4, which is pi over 2. Same answer, same volume. All right, so you can read ahead 6.2, 6.3 if you want. You don't have to, but we've got the secrets, and we're going to put it all into play tomorrow. First secret is this method, perpendicular, rectangles perpendicular. Shell method parallel. This method pi r squared. Shell method 2 pi r. Right? So we're talking about the area of a circle. We're talking about the circumference of a cylinder. Okay, that's it today. I'll fix my parametrics tomorrow. So, I mean, we've been getting done around 11 o'clock each day. I don't want to do too much more. It's too much. And then we're going to be taking quizzes at 11. So, but again, anytime you have questions for me, feel free, right? So like now is a great time if you're confused. Alex, I showed you where the videos are, right?
Yeah.
Yep. Basically, I just did 5, 5, 5.6, 5.7. We're skipping 5.8, then I did 5.9, and today we did 5.10 and started 6. Okay?